and welcome to T Academy. In today's lecture, we'll talk about generic constant coefficient differential equations. A generic constant coefficient differential equation can be written as summation k equal to 0 to n ak dk yt by dtk equal to summation k equal to 0 to m bk dk xt by dtk. Now in this equation, y of t is the output, ak's are the output differential coefficients, x of t is the input, and bk's are the input differential coefficients. Now as you can see from this equation, the output differential coefficients go from k equal to 0 to n, while the input differential coefficients go from 0 to m. The input and the output differential coefficients need not to be equal. However, the order of the system is governed by the differential coefficients of the output. So in this case, this is an nth order system. So this differential equation describes an nth order system. So for example, if I put n equal to 0 in this equation, I would get a0, and there will be no differentiation of the output, and I would get a0 y of t. This equation describes a static system or a zero order system. In the previous lecture, we solved this equation, y dot plus 2y equal to x. And if I were to compare this equation with the generic equation of a constant coefficient differential equation, then I would get a0 equal to 2 and a1 equal to 1. So this equation describes a first order system, since the order of differentiation is equal to 1. So we solved this equation in the previous lecture by finding out the homogeneous solution as well as the particular solution. If you haven't seen that lecture, then you can click this link and watch that lecture. Now you also recall from my previous lecture that we used initial conditions sometimes also used interchangeably as auxiliary condition to find out the solution of the differential equation y dot plus 2y is equal to x. So in general, for an nth order system, we require n initial conditions. So in order to solve this differential equation, we would require either an initial condition at t equal to 0, or it can be an auxiliary condition at t equal to t naught, since there is nothing sacred about t equal to 0, and we would require the values of y y dot y double dot all the way to y dot power n minus 1. So we would require n differential coefficients and the order of differentiation would be 1 less than the order of the system. Now for the case of y dot plus 2y equal to x, we saw in the previous lecture that this system was linear when the initial condition y dot was equal to 0. So this we can generalize for an nth order system. So an nth order system will be linear if and only if all auxiliary conditions vanish. That is, y0 dot y0 double dot all the way to y0 n minus 1 has to be equal in order to make the system linear. And this condition is known as the condition of initial rest. And I explained this concept in one of my other lectures on linear systems, and I also explained this with the help of an example of a dynamic system like a capacitor. So you can watch that lecture by clicking the link if you haven't seen it. So that's it for today's lecture. In the next lecture, we'll see an example of how we can solve a higher order differential equation. So thank you very much and see you in the next lecture.